So far in your world of definite integrals, you have been restricted to integrals between two finite numbers, and the integrand, or the function inside the integral sign, must be continuous on that interval. Today we're going to talk about how to deal with functions where one or both of the limits of integration are infinite, or where there is an infinite discontinuity inside of the interval of integration. So let's start with the infinite ones. So how might you begin to find the integral from 1 to infinity of x squared dx, and what would this represent? So first, I think it would be useful to sketch a picture of 1 over x squared. We only care about it from 1 to infinity. But so for example, when we input 1, we go through the point 1, 1, and this function decreases as the x's get larger and larger. So the integral from 1 to infinity would represent the area underneath that curve from 1 on and on forever. And the question kind of is like, well, if you can go forever, could that area ever be a finite number? And the answer is yes, if the area gets smaller quickly enough. And so here's how you deal with it. You know how to find integrals when the upper bound is a finite number. So we start by saying, well, the integral from 1 to infinity, 1 over x squared dx, is the same thing as the integral from 1 to b, 1 over x squared dx, where b is a large number, and we take a limit as that b goes to infinity. Do you see how by doing that we've kind of gotten around the fact that b is infinite? Because b is finite, we're going to plug that in and take a limit of the expression once we're done. So now the antiderivative of 1 over x squared, or x to the negative 2, is x to the negative 1 over negative 1. And that's evaluated from 1 to b. So that's the limit as b goes to infinity, negative 1 over b minus negative 1 over 1. And as b goes to infinity, 1 over b goes to 0, and a double negative makes it positive, so we have that this is 1. So as in the area under y equals 1 over x squared from 1 to infinity is 1. Kind of crazy, but it turns out that that function gets smaller quickly enough that that actually converges. So the way we say that is that this integral converges to 1. And converging just means that it goes to a finite number. It might be the case that this expression that you get will go to infinity, which means the area is infinite and the integral diverges. So the way you deal with, if you have a function that is continuous from a to infinity, and your upper bound is the infinite limit, you plug in b for that upper bound and take a limit as b goes to infinity. If your lower bound is the 1, and that is negative infinity, you input a value, you can call it a or b, whatever you want, and take a limit as that goes to negative infinity. And if you have an integral over negative infinity to infinity, you break it into two integrals using whatever number you want to. I tend to pick 0 because 0 ends up being a pretty easy input. But you find the integral from negative infinity to c, and that's c to infinity, and just add them together separately. All right, so 0 to infinity, e to the negative 2x dx. So we will be checking that you're using proper notation, so don't forget to write limit b goes to infinity, the integral from 0 to b, e to the negative 2x dx. All right, now the antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x. So limit b goes to infinity, negative 1/2 e to the negative 2x, and we input 0 and b. So we have the limit as b goes to infinity, negative 1/2 e to the negative 2b minus negative 1/2 e to the 0. Notice that this is the same thing as negative 1/2 e to the 2b plus 1/2. And as b goes to infinity, negative 1/e to the 2b goes to 0, so this limit goes to 1/2. So the proper thing to say is that this integral converges to 1/2. I won't be very picky about that, but you just must say that it diverges if that limit is infinity. Okay, next, how about the integral from negative infinity to infinity of 1/x² plus 1? So, well, if you graph 1/x² plus 1, you notice that this function is symmetric about the y-axis and looks something like this. So if this area is finite, that area will be finite too, and the value will be twice the value of the area on just the right side alone. So let's do twice the integral from 0 to infinity, 1/x² plus 1 dx. So that's 2 times the limit as b goes to infinity. And you can use whatever letter you want. It's just that when I learned Calculus 1, they used b's. Your book uses t's, but t's look like plus signs, so I'm going to avoid those. All right, that's twice the limit. B goes to infinity. This will be arctan, or tan inverse of x, evaluated from 0 to b. So 2 limits, b goes to infinity, times, so of arctan b minus arctan 0. And some people took a trig class and hoped really hard that they would never, ever have to know about arctan again, but that was wrong. And if you haven't had to deal with it before, that's just, you've been lucky. It does come up now. So this is what tangent looks like, at least one period of it. It has vertical asymptotes at negative pi halves and pi halves. Now arctan is the inverse of this function, which means you switch the x's and y's, which results in this graph being reflected over the diagonal line y equals x. Now when you swap x's and y's, those vertical asymptotes now become horizontal asymptotes, and they are at positive pi halves and negative pi halves, and the picture of arctan looks like this. Yes, you do have to know that, and I'm not the only person that expects that. So the reason you have to know that picture is because the picture tells you what happens to arctangent or tan inverse as your values in the arctan get very large. As arctan gets large, you travel along this part of the function and your y values approach pi halves. So this actually is 2 times pi halves. And from the picture you can also see that that dot at the origin, that means that arctangent of 0 is 0. So this integral converges to pi. Before you think that every single integral must converge, let's talk about one that does not. So you have the integral from 1 to infinity of 1/x dx. So use your notation as proper, make a limit. Limit b goes to infinity, integral from 1 to b, 1/x dx. Well, the antiderivative of 1/x is ln, absolute value of x. So ln, absolute value of x, from 1 to b. And that's the limit as b goes to infinity, ln, absolute value of b, minus ln of 1. And ln is another graph that a function you should know what the graph looks like. ln is the inverse of e to the x. So e to the x looks like this, roughly speaking. That point is the point 0, 1. ln looks like this. And it's an example of a function that grows, but grows very slowly. But the point is as b goes to infinity, this ln keeps getting larger and larger and larger. So this limit is infinity, and this diverges. WebAssign note, I'm pretty sure they want you to write in diverges in all caps. I'm not certain if that's right, but I've seen that in answer keys, so just be careful with that. Next, let's tackle a problem in which the bound is negative infinity and where you have to use a semi-more advanced integration technique to find the antiderivative. So given x e to the x, since we have a product, the integration technique that you have to apply here is parts. So we're going to integrate by parts. This is the most basic one. We'll let u equal x. dv will equal e to the x dx, making du into dx and v into e to the x. So this is the same thing as the limit. B goes to, in this case, minus infinity, lower bound b, upper bound 0. And be careful with notation here, because part of your integral, when you apply integration by parts, is no longer going to have it's no longer going to have an integral sign, so you've got to put bounds there. So uv x e to the negative x, positive x, excuse me, that's from b to 0, minus the integral from 0 to b of v du, so e to the x dx. Okay, and then it's quite tricky with negative signs, so just be really, really, really slow and conscientious and careful. So first you plug in 0, first term is 0, minus b e to the b, minus e to the x evaluated from 0 to b, which is the same thing as the limit as b goes to minus infinity, negative b e to the b, minus parenthesis e to the b minus e to the 0. A lot to keep track of here. And we're going to be done with the some of the tricky stuff. B goes to minus infinity, negative b e to the b minus e to the b plus 1. Okay, and from there just pause and make sure that you understand where all the negative signs came from and all that. Now, before you rush ahead and say this is infinite, it's a little bit different because b is going to negative infinity, not positive infinity. So you have to think about how do you deal with negative infinity and what does that mean? And this is the easiest explanation that I could come up with. When you go to negative infinity, you plug in very, very, very large negative numbers. So those numbers have two components. They're huge and they're negative. And what you can do is you can incorporate for those things separately. You can take into account the large by sending your b to positive infinity. That will make the numbers big. And then you can make them negative by taking all of your b's and making them into negative b's. So that'd be negative, negative b, e to the negative b, minus e to the negative b, plus 1. Or you can think plugging in negative 1 million will be the same in this upper expression as plugging 1 million into this bottom expression. So that's my general way to deal with negative infinity, is change the variable to its opposite and change the negative infinity to positive infinity. I hope that's understandable. All right, now simplifying slightly, this becomes the limit as b goes to infinity, b over e to the b minus 1 over e to the b plus 1. Now you can limit each term individually. I'm going to hold off on the first one for just a second. The second term, this 1 over e to the b, that's going to go to 0, and the last term stays at 1. Now, There is a rule that lets you deal with limits that are of the form infinity over infinity. It's called L'Hopital's rule. L'Hospital, it's French and it's spelled like hospital. And different classes teach that in Calculus 1 versus Calculus 2. Your textbook explains it in Calculus 1, which is section 4.4 if you haven't seen that before. If you have seen that before, great. If you haven't, here is how it works. So as b goes to infinity, the numerator goes to infinity and so does the denominator. What that rule tells you that you can do is instead you can limit the ratio of the derivatives. So the derivative of b is 1. The derivative of e to the b is e to the b. And then you can limit that function instead, and those functions' limits are equal. I kind of think about it as the quotient rule that students wished was, even though it's totally not a quotient rule. And it only works if your limit is of the form infinity divided by infinity. You could have positive infinity divided by negative infinity, but both limits must be infinite. Or you have a limit that's of the form 0 over 0. It also works for those. So if you need to know more about that, take a look at section 4.4, and if you have troubles, let me know. And now you can determine that 1 over e to the b, that's going to go to 0. This limit is 1. This section is a great time to practice some other integration techniques again, so it's good to know. All right, now we had an example of the integral from 1 to infinity of 1 over x squared, and that converged. And then we had an example of 1 to infinity of 1 over x, and that diverged. And so the question is if you have 1 over x to some number, when will that integral converge and when will that diverge, and what number is sort of like the tipping point to which something that is finite becomes infinite? And interestingly enough, it is the integral from 1 to infinity of 1 over x. That is sort of the boundary point, but we're going to actually prove it. So the first thing that we know is we know that the integral from 1 to infinity of 1 over x dx, we know that diverges. So diverges if the power is equal to 1. So that is, in these notes, example number 3. So what we're going to do is we're going to assume that p is not equal to 1, so some other number. And then you just integrate the integral to infinity 1 over x to the p dx will equal the limit as b goes to infinity, integral from 1 to b, let's say x to the negative p dx. Then we can apply our power rule. So this will be the limit as b goes to infinity, x to the negative p plus 1 over negative p plus 1 from 1 to b, which will be the same thing as the limit b goes to infinity, and then plug in your b for your x. B to the negative p plus 1 over negative p plus 1 minus, well, 1 to the negative p plus 1 will be 1, so 1 over negative p plus 1. Now there is a greatest common factor of 1 over 1 minus p. Let's factor that out. Say the limit as b goes to infinity, 1 over 1 minus p times b to the negative parenthesis p minus 1, just taking out a negative sign, minus 1. Or putting the b thing in the denominator, that will look like this. Limit b goes to infinity, 1 over 1 minus p, 1 over b to the p minus 1, minus 1. And let's just pause for a second and make sure you understand where that all came from. Now let's consider what happens if that p is both greater than 1 or less than 1. So first, the greater than 1. And you can think an example of a number that was bigger than 1 was 2. And so you'd assume that, probably this one's going to be the one that converges, and here is how you prove it. So if p is bigger than 1, this implies that p minus 1 is bigger than 0. So my power is bigger than 0. And as b goes to infinity, something to a positive power, that positive power being p minus 1, that's going to go to infinity as well. And if that goes to infinity, 1 over that thing is going to go to 0. And so then the limit will be -1 over 1 minus p. Or that's the same thing as 1 over p minus 1. You get that by multiplying the numerator and denominator both by -1. Now, if p is less than 1, well, that tells you that p minus 1 is less than 0. So think about what that means. That means that this thing, the power is negative. So you have like 1 over something to the 1 over b to the -2, which actually reciprocates and puts it back in the numerator. So what that means is that 1 over b to the p minus 1 is the same thing as b to the 1 minus p. And that's going to go to infinity. So this will diverge. So in summary, if the power in the denominator is bigger than 1, it's like 1 over x to the 1.1, 1 over x to the 1.7, 1 over x to the 6th, those will converge. When it's smaller, like 1 over x to the 1/2, 1 over x to the 0.7, those will all diverge. And if they're negative, it's pretty obvious that they're going to diverge. Like 1 over x to the -2 is the same thing as x squared. Just looking at a picture of x squared from 1 to infinity, it's pretty obvious that that area is definitely going to be infinite. All right, next let's deal with some improper integrals that have infinite discontinuities. So this says that if the infinite discontinuity happens at the right side of your interval, so you have this interval from a to b, you have to come at that b number from this side. That's what this means. The number c you have is less than that b number. And if the number that you are discontinuous at is at the other end, you have to come at it from the right, hence the whole going to a plus. And if there's some c in the middle, then you're going to have to do the sum of two integrals using that c as a breaking point. Now just note that if either of these diverges, the whole thing does. So for this integral to converge, both must converge. And if you get lucky and you prove that the first one diverges, there's no reason to check the second one. And we'll have an example where you see something like that. And one thing we'll be testing when we're looking at your work is, can you pick out the right kind of one-sided limit to apply in various cases? All right, so this one, think about what is the problem point. And the problem point is x equals 0. So in your interval from 0 to 8, you have to come at 0 from the right side. So this is the limit as b goes to 0 from the right, that's 0 plus the integral from b to 8. And I'm going to make that x to the -1/3 dx. If you get the right answer but don't use the right notation, you're not going to get full credit. So we have the limit as b goes to 0 plus. Now the antiderivative of x to the -1/3 is x to the 2/3 times 3/2. It's evaluated from 8 to b. So first we input 8 and then we input b. Limit b goes to 0 plus 3/2, 8 to the 2/3 minus 3/2 b to the 2/3. Okay, so that will be 3/2 times, now 8 to the 2/3. First you cube root 8, which makes 2, then you square it, which makes 4. And I wrote no limit sign because in this step I'm also limiting this thing. Since b goes to 0, 0 to the 2/3 is in the numerator. That's okay, it's 0, so that last term is just 0. And I think that this limit is going to be 6. All right, next let's consider this one, 1 over the root of x minus 2. So once again, the problem point is our lower bound. So x equals 2 is the problem. So we have to come at 2 from the right side. So that's the limit. As b goes to 2 from the right, the integral from b to 5, x minus 2, the quantity raised to the negative 1/2. So the antiderivative of x to the negative 1/2, well, that's x minus 2 to the positive 1/2 times 2, evaluated from 5 to b. So now inputting our stuff and making that power of 1/2 back into a square root. So that's 2 square root of 5 minus 2 is 3, minus 2 square root b minus 2. And now you can plug in 2. 2 is 2 positives, a little bit bigger than 2, so this will be an expression that's awfully close to 0, but is positive, so you can actually square root it. And this just goes to 2 root 3. It's really easy to spot improper integrals when you have something that's improper because it has an infinite bound. The ones where there are infinite discontinuities, meaning the function is not defined at some point in time, those are a little bit trickier to spot, so just be careful and don't get duped. All right, secant of x. Well, the first thing that helps to remember is that secant of x is 1 over cosine of x. Also helpful to know what a picture of secant looks like, but I must admit that even I kind of forget sometimes. So take cosine. So cosine of 0 is 1. Cosine is 0 at pi halves and at negative pi halves. And of course it does other stuff, but that's kind of what sum of cosine does. That pattern repeats. Now secant is the reciprocal of that, meaning you take 1 divided by those numbers. And obviously these numbers are going to give you asymptotes. They're going to be 1 divided by 0. This number up top is 1 divided by 1, gives you that point. And then think as you go this way along the picture, you have 1 divided by small positive number. That makes very large infinite number. Same thing on the other side. Looks kind of like parabola-ish, except for parabolas do extend outwards, and this one is sort of fenced in by those asymptotes. So you can see from that picture that with the integral of secant, the problem is the pi halves point. 0 is fine. So this integral, and also this time it's the right endpoint that's given us troubles. So we have to come at pi halves from the left. So that's the limit as b goes to pi halves from the left, integral 0 to b secant x dx. And you don't have to memorize this formula, but you might end up doing it whether or not you want to because it comes up often enough. The antiderivative of secant is ln absolute value secant x plus tan x, evaluated from 0 to b. So that's limit b goes to pi halves from the left, ln absolute value secant b plus tangent b minus ln absolute value, which is not going to fit, so I'm going to find out what these are. Secant of 0 from the picture you can see is 1. Tangent of 0 is going to be 0. Okay, now we need to figure out what happens as b goes to pi halves minus from the left. So this term, that's going to go to infinity. Now tangent, if you know what that looks like, also goes to infinity. So the number inside the natural log is going to infinity. So that first term is going to be infinite, minus ln of 1, which is 0. So this is infinite, meaning that that particular integral diverges. All right, as promised, here is an example where the point that is a problem is not an endpoint but in the middle. So we have the integral from 0 to 3 of 1 over x minus 1 dx. So x equals 1 is the problem point. So we find this by finding the integral from 0 to 1 over x minus 1 dx, plus the integral from 1 to 3, 1 over x minus 1 dx. And evaluate each of those separately. So first let's do the integral from 0 to 1, 1 over x minus 1 dx. So for that particular problem, the problem point is 1, which is the upper bound. So we have to take the limit as b goes to 1 from the left, integral from 0 to b, 1 over x minus 1, which is the limit as b goes to 1 from the left, ln absolute value x minus 1 from 0 to b, or the limit as b goes to 1 minus ln absolute value b minus 1 minus ln absolute value negative 1. Now this part, so the thing inside the b minus 1, that's going to 0. And it's being absolute valued, so we know that it's positive. So here's what the picture of ln of x looks like roughly. So as the x goes to 0, look at what happens to ln. It goes down forever and ever and ever, as in it goes to minus infinity. So this limit is actually negative infinity, which means the whole integral diverges. If one of the components of that diverges, the whole thing does, no matter what happens to that component. So you're done. Had this first one converged, you'd have to also figure out the second portion and then add the results together for the overall integral, unless the second integral diverged, in which case your whole integral also diverges. The last topic in this lesson is something called the comparison theorem. And this theorem will have parallels to something we discuss in a later chapter, sequences and series, when we're doing tests for convergence and divergence there. Something a little bit similar. So suppose you have two functions f and g, and they're continuous, and from some point a on, the function f of x is above g of x. And also both functions are positive, that matters as well. So here's the general picture. There's your a value. You have your function f of x. And that function f of x lives above g of x, who chooses to do some crazy stuff, but f of x was always bigger than or equal to g of x. And the question is what can you conclude about these things based on the behavior of one function? And these should be pretty logical if you think about them. If the integral from a to infinity of f of x dx is convergent, notice that that is the bigger area. If the bigger area is convergent, well then so is the smaller area. Absolutely has to be. And then reverse it. If the smaller area diverges, as is meaning it's infinite, well then so is the one that's even larger than that. It takes a little bit of practice to figure out what way to do the comparison, but I think that this is pretty darn logical if you think about it that way. If the bigger one converges, the smaller one has to converge too. If the smaller one diverges, the bigger one has to do so as well. So now we're going to show that e to the negative x dx is convergent. And what does this imply about the convergence or divergence of the integral from negative infinity to infinity of e to the negative x squared? Just a note about this particular integral. If you ever take a statistics class, I'm pretty sure that that is the integral that gives you this bell curve and gives you all those numbers that are in your t tables and z tables and stuff like that. Particularly, I think it's the z tables that comes from. And this is an integral that you cannot compute using traditional methods. You can actually prove that it's not possible to find an antiderivative of e to the negative x squared. You have to estimate it somehow. Okay, so first of all, that second integral goes from minus infinity to infinity, and the first one goes from 0 to infinity. So what the heck? So what you should note, first of all, is that the function y equals e to the negative x squared, this thing is even, has symmetry about this would be the y-axis. So the integral from minus infinity to 0, e to the negative x squared dx, will equal 0 to infinity, e to the negative x squared dx. Meaning if we show the latter converges, so does the former. And the original as a result. Okay, so that's the first thing to note. Now, the second thing to do is to look at a bit of a picture. If you look at a picture of e to the negative x and e to the negative x squared, here is what happens. Both go through the point 0, 1. So that's what e to the negative x looks like. And up until 1, they're actually equal. Or not equal, up until 1, the e to the negative x squared is above that curve. A little bit like this. It's a bit exaggerated, but that's approximately what it looks like. So you can tell that from 1 on, e to the negative x squared is below e to the negative x. And so one thing you want to note is that the integral from 0 to 1, e to the negative x squared dx, is finite. You could technically make like a box and show that it's less than 1, but it's a finite number, not infinite. And so what you can also note is that since for x's that are bigger than or equal to 1, negative x squared is less than or equal to negative x. And then also, e to the negative x squared is going to be less than or equal to e to the negative x. And so we can use our comparison theorem to show that if the integral from 1 to infinity, e to the negative x, converges, so does the second one. And so the integral from 1 to infinity, e to the negative x dx is equal to the limit as b goes to infinity, 1 to b, e to the negative x dx. This is the limit as b goes to infinity, negative e to the negative x, evaluated from 1 to b. Now first plug in b, and we have the limit as b goes to infinity, negative e to the negative b minus negative e to the negative 1, or the limit as b goes to infinity, negative 1 over e to the b plus 1 over e, and that is equal to 1 over e. And so then you can say that as the integral from 1 to infinity e to the negative x dx converges, by comparison, so does the integral from 1 to infinity e to the negative x squared dx, and thus the integral from minus infinity to infinity e to the negative x squared dx converges as well.